Selamat datang di Fakultas Matematika dan Ilmu Pengetahuan Alam Universitas Negeri Makassar. Fakultas Matematika dan Ilmu Pengetahuan Alam Universitas Negeri Makassar adalah salah satu ikon kemajuan Universitas Negeri Makassar. Gedung FMIPA UNM yang diselesaikan pada tahun 2021 oleh Kementerian PUPR diresmikan langsung oleh Rektor bersama pimpinan Balai Prasarana Pemukiman Wilayah Sulawesi Selatan Kementerian PUPR. Dengan luas mencapai 5.376 meter persegi, Menara FMIPA UNM berdiri megah setinggi 12 lantai. Gedung ini memiliki berbagai fungsi, mulai dari kantor dekan, unit layanan terpadu, laboratorium, ruang rapat, ruang senat, ruang teater, hingga kelas perkuliahan modern, mencerminkan semangat Universitas Negeri Makassar dalam menyediakan fasilitas pendidikan terbaik. Menara FMIPA UNM tidak hanya menjadi simbol kemajuan, tetapi juga representasi komitmen universitas dalam mendukung perkembangan ilmu pengetahuan dan teknologi di wilayah Indonesia Timur. Lingkungan kampus yang asri di FMIPA UNM dilengkapi dengan fasilitas pendukung berupa 3 taman hijau yang terawat, lapangan olahraga yang mendukung aktivitas mahasiswa, taman baca di setiap jurusan untuk mendukung minat baca mahasiswa, serta area parkir yang luas. FMIPA UNM berkomitmen untuk menjadi unggul secara nasional dan berdaya saing global dalam pengembangan bidang MIPA dan pembelajaran, serta menghasilkan alumni yang kompeten dalam bidangnya, literate dalam teknologi informasi, dan berwawasan kewirausahaan. Dosen di FMIPA UNM saat ini berjumlah 259 orang dengan 45 profesor, 38 associate profesor, serta 116 orang berkualifikasi akademik doktor. Dengan sumber daya manusia yang kompeten, FMIPA UNM menyelenggarakan pendidikan berkualitas tinggi yang telah menghasilkan lulusan yang kompeten dan siap bersaing di dunia kerja, baik di tingkat nasional maupun internasional. Dalam mewujudkan Tridharma Perguruan Tinggi, Fakultas Matematika dan Ilmu Pengetahuan Alam Universitas Negeri Makassar memainkan peran penting dalam masyarakat melalui berbagai aspek, termasuk pendidikan, penelitian, dan pengabdian kepada masyarakat. Dalam bidang pendidikan, FMIPA UNM melaksanakan pendidikan yang berkualitas tinggi dalam bidang matematika, fisika, kimia, biologi, geografi, dan statistika yang membentuk dasar pengetahuan yang kuat bagi mahasiswa. Fakultas Matematika dan Ilmu Pengetahuan Alam Universitas Negeri Makassar saat ini memiliki 5 jurusan dan 16 program studi yang telah terakreditasi A, unggul, dan juga terakreditasi internasional ASIIN. Jurusan Matematika berkomitmen untuk menyediakan tenaga ahli di bidang pendidikan dan penelitian bidang matematika melalui 3 program studi, yaitu Program Studi Matematika, Program Studi Pendidikan Matematika, dan Program Studi Sains Aktuaria. Jurusan Fisika memadukan pendidikan berkualitas dengan pengembangan teknologi. Jurusan Fisika menyediakan 2 program studi, yaitu Program Studi Fisika dan Program Studi Pendidikan Fisika. Jurusan Kimia berfokus pada pendidikan inovatif di bidang kimia dengan program studi kimia, pendidikan kimia, dan program studi sains lingkungan. Jurusan Biologi. Jurusan ini mengintegrasikan pendidikan, penelitian, dan konservasi bidang biologi. Jurusan Biologi menyediakan 3 program studi, yaitu Program Studi Biologi, Program Studi Pendidikan Biologi, dan Program Studi Bioteknologi. Jurusan Geografi berkomitmen untuk menghasilkan lulusan yang profesional dan kompeten di bidang pendidikan geografi, melek teknologi informasi, serta memiliki wawasan kewirausahaan. Jurusan ini memiliki 3 program studi, yaitu program studi geografi, program studi pendidikan geografi, dan program studi sains informasi geografi. Program studi pendidikan IPA. Program studi ini berfokus pada pembelajaran yang mengintegrasikan berbagai cabang ilmu IPA seperti fisika, biologi, dan kimia sehingga menghasilkan lulusan yang mampu memberikan pendidikan holistik dan relevan bagi siswa sekolah menengah pertama. Dengan komitmen terhadap kualitas pendidikan, program studi pendidikan IPA telah berhasil meraih akreditasi unggul, sebuah pencapaian yang mencerminkan standar tinggi dalam pengajaran, kurikulum, serta fasilitas pendukung akademik yang ditawarkan. Program studi statistika. Program studi statistika berkomitmen untuk menghasilkan lulusan yang memiliki keahlian tinggi dalam bidang statistika, serta mampu menerapkan analisis data secara efektif di berbagai sektor. Untuk memastikan visibilitas tinggi bagi penelitian yang dipublikasikan, FMIPA UNM mengelola 10 jurnal ilmiah yang menjadi wadah publikasi penelitian berkualitas tinggi di berbagai bidang ilmu pengetahuan alam, pendidikan, dan teknologi. Setiap jurnal ilmiah di FMIPA UNM dirancang untuk mendorong perkembangan ilmu pengetahuan melalui kajian empiris, teoritis, dan pengajaran yang terindeks di berbagai basis data ilmiah, nasional, dan internasional. Dalam rangka memperkuat posisi FMIPA UNM sebagai institusi pendidikan tinggi yang berdaya saing global, FMIPA UNM memiliki jaringan kolaborasi yang luas dengan berbagai universitas terkemuka di dunia. Kerjasama ini mencakup pertukaran mahasiswa dan dosen, penelitian bersama, serta pengembangan kurikulum berbasis global. Dengan jaringan kemitraan yang luas, Fakultas Matematika dan Ilmu Pengetahuan Alam Universitas Negeri Makassar terus berinovasi untuk menghasilkan lulusan yang mampu bersaing di pasar kerja internasional. Sebagai penopang kemajuan pendidikan di kawasan timur Indonesia, Fakultas Matematika dan Ilmu Pengetahuan Alam Universitas Negeri Makassar memiliki harapan besar untuk terus menjadi pusat pengembangan ilmu pengetahuan dan teknologi. Gedung megah ini dengan segala fasilitas dan semangat yang diusungnya menjadi simbol tekad untuk mencetak generasi unggul yang siap bersaing di tingkat nasional dan internasional. Dengan lingkungan yang inspiratif, staf pengajar yang berdedikasi, dan mahasiswa yang penuh semangat, Fakultas Matematika dan Ilmu Pengetahuan Alam Universitas Negeri Makassar terus melangkah maju, memberikan kontribusi nyata untuk masyarakat, bangsa, dan dunia.
How are you?
Sound. I'm fine. How about you?
Fine.
Yeah.
How about
The keynote from Malaysia.
I am sorry,
Yeah.
I couldn't attend because the time difference is 5 hours.
Yes.
That means that in the midnight,
Yes.
your
of
morning
course.
session in
Yeah.
Turkey.
It's okay.
Yeah. Hello
We
to
can start.
everyone.
Yes.
If you want, yeah, sure.
Okay, we can start. I think Mutia.
Yes, sir. Okay.
Thank you very much, Nazife. Yes.
Actually, thank you very much for inviting me.
Are you welcome?
Okay. Welcome back, ladies and gentlemen. Now we will start the second keynote speakers of the conference. The second session of the conference will be moderating for Mr. Arfa MSc. He is lecturer from the Mathematics Department, Faculty of Mathematics and Natural Sciences, Universitas Negeri, Makassar. In this session, we will have three outstanding academics as keynote speakers. The first, Associate Prof. Gultuk from Turkey. The second, Associate Prof. Dr. Nazif Erkurs Özkan from Turkey. And the last is Gihan Eriksel from Turkey. Okay, so without further ado, I will like to head over the session to the moderator.
Okay. Thanks to the moderator for handling over the session to me. And good afternoon, everyone. And good morning for Associate Professor Dr. Nazifi in Turkey right now. Host geldiniz hocam. And I'm Arfa, and I'll be the moderator for today's event. We are honored to have our distinguished keynote speaker, Associate Professor Dr. Nazife Erkusun Özcan, from the Mathematics Department of the Faculty of Science, Hacettepe University in Ankara, Turkey. So before we begin, I would like also to thanks for all the organizing committee, sponsors, and all participants for making this event possible and successful. And today's international conference promises to be a day of rich of discussions and valuable exchange of ideas. So to maximize our value of our time together, we will begin our session where our keynote speaker will deliver his research in our field tour room. Following the presentation, we will have a Q&A session. So first of all, let me introduce our esteemed keynote speaker, Associate Professor Dr. Nazife Erkusun Özcan is a faculty member of the Faculty of Science, Mathematics Department of Hacettepe University, Ankara, Turkey. Her research focus is in functional analysis, including semigroup theory, operator theory, and also in ergodic theory, including mean ergodicity, spatial operator nets, and also perturbation theory. She has already published a lot of papers on very well reputed journals. For example, in this year, in 2025, she together with Mukadov F published a paper with the title of "On the Uniform Zero-2 Law for Positive Contraction on Abstract State Space Positivity" at the Journal of Positivity, volume 29, number 18. She also, beside that, she also have win a lot of projects, research projects, and also bring many papers on the international conference. Well, without further ado, please join me in welcoming our keynote speakers, Associate Professor Dr. Nazife Erkusun Özcan, and the time is yours.
Thank you very much for a nice introduction. And hello to everyone from Turkey. And first of all, of course, I would like to thank the organizers, especially Dr. Jafaruddin. And we know each other for a long time, and I hope that we can meet one time face to face next year or over next year. And as you said, I am interested in functional analysis, operator theory in general, or positivity. Actually, the behavior of operator semigroups, what I want to talk about today also. And if you are interested in, you are welcome to contact with me. May I share my screen? Okay. You can. Yes. Yeah. You can find me from my personal web page, and you can see my Gmail and Hacettepe email. You can write both of them, any one. If you are interested in functional analysis or operator theory, semigroup theory, you are welcome. And also during my talk, you can don't hesitate to interrupt me. Please ask your question, not to wait the end of the talk. And today I am going to talk about the Markov semigroups and their uniform ergodicity properties. First of all, we will we will work on a spatial space, which is called the abstract state space. First of all, let us discuss what is the abstract state space. You know, in the functional analysis, we know many spatial spaces, L1, LP spaces, or sequence spaces, or C01, etc. Now, we have only in functional analysis case, we have just interested in the norm. Now we have norm space. We put on that space an order. The order comes from the positive cone. What I mean, you have here like X, you put on it less than or equal such an order, which is poset. X is less than or equal Y, means Y minus X is positive. Positive means we have a positive cone. Therefore, that positive cone creates us an order on that normal space. And also, it is called, if that norm space is ordered vector space, norm space, the norm on X plus is additive. What it means, X plus Y, both are positive. It is additive, norm X plus norm Y. And also regular. Regular, you take any element from the open unit ball. You can find any element, positive element again, from the closed unit ball. That means that line minus Y and Y. X is you can create a line and beginning point minus Y and end point Y, and X is on this line. Then that space is called abstract state space or base norm space. In this setting, the closed positive cone is always lambda generating. Lambda is bigger than 1. What it means? If you have any element from the space, sorry, that is my mistake. It is not E, it is X or E. You have, just call it E. You have any element X, you can write X as a difference of two positive elements, Y minus Z, and Y plus the norm of Y plus the norm of Z is less than lambda times norm X. Basically, if you have a strict positive linear form on X, that means you have a linear operator from X to R, which is positive. It means sends every positive elements to positive reals. Then you can create a base from the positive cone as follows, like here, where actually it is the boundary of the unit ball, and also depends on the functional F. Then in this case, we have, if the K union minus K, consider the set K, consider another set minus K, that means X and minus X, all elements, and take the closed hull, the combination of finite elements with lambdas, and the sum of the lambdas are equal to 1 always. Then if that closed convex hull, that convex hull, there is, yes, right, that closed convex hull is the closed unit ball of the space, X, then that space is called strong abstract state space. Basically, in this case, we have additivity always on the norm, as written here. What is an example? The classical example is the standard L1 space, integrable function spaces with the one norm. Or you have ordered normed space. As I told you, we have a norm and we have an order, and there is an order unit. What it means, the order unit? For every element, where is my hand? I lost my, yes. For every element F, let's say, for every element from the space X, you have one lambda such that plus minus x is always less than or equal lambda e. What is e? E is your order unit. Where is the which space has an order unit like C01? If you consider the functions, continuous function from 0, 1 to real number, which is continuous. Since your domain is closed and bounded, basically convex, then f is bounded function. So you can write f always, or plus minus f, always less than or equal lambda times constant function 1. What is lambda from here? It is the supremum of the value of f of x. So the space of C01 is ordered normal space with an order unit. And the dual of that space is an abstract state space normally. And the last example, the basic last example, for an arbitrary Banach space, we can create a base norm or abstract state space in this form. You can take the direct sum of real numbers plus x and put as a norm on lambda x is the maximum of lambda and the norm of x. And the positive cone of this space is the norm of x is always less than or equal lambda. Then that space also, for an arbitrary Banach space, you can create a base norm space. Okay, we have now our space, which is called abstract state space. And we need an operator, especially the Markov operator. Now consider it is our space. X, positive cone, base, positive functional. And now you have depends on some of the books called linear operators. Some of them just call operator. Operator means linear mapping. Now we have here linear mapping T from X to X. It is positive means we have positive cone here. We can say positive elements, take the positive elements and send to positive elements also. Tx is positive. It is actually the positive cone invariant under T. That PEP, that linear operator or just basic operator is called positive operator. And you have now positive operator and T is, we need also Markov case. We have Markov operator when if the base K is invariant under T. That means you take every element from K, sends to also the base K. In that case, operator norm of T is always 1. And the adjoint mapping, the dual mapping, is satisfy the condition, that condition, T star F is equal to F. It means our functional at the beginning to help to create the abstract state space is a fixed point for the T star. And don't forget, this is abstract state space and the dual is ordered Banach space with the unit F. Now, if you have an arbitrary contraction, can you create a Markov operator? Yes, of course, like a Banach space case, you have a Banach space X, you have a contraction from X to X. If you remember from the previous slide, we create a abstract state space in this form and consider the new operator T is like lambda X sends to lambda Tx. Then it becomes a Markov operator. Always, if you have a Banach space, if you have a contraction, then you can construct abstract state space and Markov operator. What we need basically Dobroshin ergodicity coefficient. Actually, it is directly the operator norm of the restricted operator T on the kernel space of F. What it means, that N is actually the kernel space of F. Take every element and send to 0. And now you take T restricted to kernel F and consider the operator norm. consider the operator norm of that the new restricted operator T. It is called Dobroshin ergodicity coefficient. Or we can formulate in this form. You are familiar from functional analysis lecture. Why it is important? If that coefficient is less than 1, then the iteration of Tn, t squared, t cubed, t to the power 4, and etc., converges to an invariant distribution with exponential rate. I will explain all of them. But there are some problems just if we focus on the Dobroshin ergodicity coefficient. But first of all, I will just give to you such set. P is projection, T is Markov, and commutative with P. Now, what is the new definition? And I will explain what do we need the general version of the Dobroshin ergodicity coefficient. Now you have abstract state space, you have a linear bounded operator, you have a projection. Projection means P square is equal to P. And the Dobroshin ergodicity coefficient again is the operator norm of the restricted operator T on the kernel of P. The kernel space of the projection P. If you take the identity as a projection, that one is always equal to 1. And that quantity is called the generalized Dobroshin ergodicity coefficient of the operator T with respect to projection P. And if you take as a projection like rank 1 operator, what it means, if T is, where is it? If P is Ty0, that means Px is equal to Ty0, which is equal to f of x times y0. It is real number. And actually, that operator now takes arbitrary x and sends to lambda times alpha times y0, one-dimensional space. So it is called rank 1. Then that Dobroshin ergodicity coefficient is equal to the generalized Dobroshin ergodicity coefficient for a special case. Okay, if it is a special case, why do we need that definition? If you look at that example, consider the operator T, which is Markov, because if you sum all rows, all rows, they are equal to 1. We are basically on R cube, Rn, always abstract state spaces. Then it is convert. Actually, where is the problem? We want to use that coefficient to characterize ergodicity properties of the iteration of Markov operators. The expected idea was if that operator converges to projection, then the Dobroshin ergodicity coefficient should be less than 1. But in that example shows us that it is not correct. You have T, it converges uniformly to a projection, this one, but the classical Dobroshin ergodicity coefficient is equal to 1. Therefore, we needed the new general version, and they defined, Mukhomedov and Ahmed defined the generalized version. And what they proved, if you have T and S, remember that formula, T and S are Markov operators, commutative with P, P is projection, and satisfy that condition, then all are true. But the Dobroshin ergodicity coefficient always take the value between 0 and 1. And the difference of two operators' coefficients are less than or equal to the difference of their norm. It is some kind of triangle inequality. And if you have an arbitrary bounded operator H, which is commutative with P, then the multiplication of T of H, the coefficient of multiplication of two operators T and H is always less than or equal multiplication of operator norm of H and the Dobrosch-Energeticity coefficient. Additionally, here, if you look at here, H is only bounded operator. Moreover, if Hs or S is Markov operator, then we have that inequality also. The coefficient of multiplication to operator is always less than or equal multiplication of their coefficients, Dobrosch-Energeticity coefficients. Okay, now what we have? We have Dobrosch-Energeticity coefficient, Markov operator, and abstract state spaces. But we need an C0 semigroups also. Now take, I need my pen. Let us go back to calculus. You have any function from 0, infinity, the positive part of real numbers to L of X. X is Banach space. L of X is the all operators from X to X bounded. There is an operator norm. Moreover, since X is Banach space, that linear operators collection L of X with the operator norm. What is the operator norm? Let us remember again. Supremum of T of X, where X is the element of Banach, unit ball of the space X. Then it is Banach space, because X is also Banach space. Now, what that function is doing? Take the T and sends to the operator TT. TT is bounded operator, defined on X. Now, what we have? First of all, it has to take 0 and sends to identity. That means T0 is equal to identity. And if you consider any T and S, and take T plus S, T is positive, S is positive, T plus S is positive real number. It sends to operator T plus S with the index T plus S. That operator must be equal to composition of multiplication of TT and TS. It is algebraic condition. Now we need one more topological condition. What it means, for every x from the space, TTX must converge to x as t goes to 0. Actually, let us formulate by using that function. Limit t goes to 0 from right-hand side, because our domain positive real numbers, Ct minus Kc0 for every x is equal to 0. Kc is continuous with respect to strong operator topology, basically. As I told you, the first two axioms are algebraic and the last one is topological. Therefore, that collection of the operators, it is actually the collection, like TT, such that T is bigger than sometimes I lost my mouse. T is bigger than 0. TT is a collection, and that collection of bounded operators becomes a strongly continuous one parameter semigroups, or basically C0 semigroup. I can't do anything now. What is wrong? Now what we have? Now we have projection. We have Markov semigroup. That means all our operators on the C0 semigroups are Markov, and also they are commutative with the projection P. Now we want to make all of them into one case. We have TT semigroups, they are Markov operator, they are commutative with the projection P, and P is the projection on the abstract state space X. Then, if we have such semigroup, C0 semigroup, then we have the following proposition. First of all, remember, any element is a fixed point or stationary point. That means that X0 is a fixed point for each element of TT. For each element of the Markov operator T, fixed element of the Markov operator TT. Now, what the proposition says, if you have an abstract state space, you have a projection P on the space X. If you have a Markov projection, Markov C0 semigroup, which is commutative with the projection P, and if there exists T0 such that the Dobroshin ergodicity coefficient, generalized Dobroshin ergodicity coefficient of TT0 is less than 1, then that semigroup converges to 0, depends on the projection P. And now I will define one more set, which is the C0, the set of all C0 Markov semigroups denoted by CX. And we have a projection. If that Markov semigroups commutes with the projection P, I will define in CPX. I will use both notation. Now, we need the ergodicity properties, because our aim is to characterize uniform or strong P ergodicity of the C0 Markov semigroups by using the Dobroshin ergodicity coefficient. First of all, we need to define what is P, uniform P ergodicity. Uniform P ergodicity means TT converges to P in uniform operator topology. It means TT converges to P with operator norm. ST goes to infinity. ST blows up to infinity. If P is rank 1 projection, that what I told you, like TY0, then uniformly P ergodicity means uniformly ergodic. It is called uniformly ergodic. Then the theorem is given for me and myself and Faruk Mukhamedov. We have abstract state space. We have a Markov projection. It is projection, and additionally, it has to be Markov. And tau is Markov C0 semigroup. How we characterize uniform P ergodicity for the C0 semigroups? Like this one. If we have a uniformly P, if tau is uniformly P ergodic, then there exists one element TT0, which is Markov. Their generalized Dobroshin ergodicity coefficient is less than 1. And moreover, we found a exponential bound value for TT minus P. It means that TT converges to P with this rate, C times e to the power minus alpha t. Alpha is any real number and C is any real number. Therefore, we said also the following conditions, which are equivalent if the semigroup is uniformly P ergodic. If the semigroup is uniformly P ergodic, then the operator TT0, if you consider the discrete C0 semigroup case, what it means TT0, identity, the first element, the second element TT0, the third element TT0 square, the fourth element TT0 cube, an iteration of TT0 also converges to P in uniform operator topology. And also there exists a subsequence indexed by Tn, that the new Markov sequence also converges to projection P with respect to uniform operator topology. If you look at that lemma, 1 implies 2 because TT, why? Where is my pen? Because what we know, TT minus P converges to 0 as T goes to infinity. If you take an arbitrary TT0 and it is the iteration TTN, actually, if you remember TT0 and n times TT0. But the semigroup property, if you remember, T plus S is equal to TT times TS. Therefore, TT0 times TT0, T0 plus T0. One more multiplication plus T0. One more multiplication plus T0, it is equal to n times T0, which is an element of the semigroup TT. If you remember, if the sequence converges to somewhere, every subsequence must converge to somewhere also. Therefore, 1 implies 2. And 2 implies 1. Take n times T0 as a subsequence Tn indexed by Tn. So 2 also implies 1, 3. But the most important case, 3 implies 1. So let us go. 3 implies 1. Assume 1 is failed. What it means? Again, 1, what 1 say us TT converges to P. I guess something technical. If someone wants to come in the room, I lost my pencil or mouse control, but it is, I guess, because of my computer. Now I have mouse. TT minus P converges to 0. It is the uniform MIPA ergodic definition. Now, what 1 fails, so it shouldn't go to 0. Therefore, it has to take one of subsequence, let's say Sj minus P, Tsj is not converged to P. In the uniform operator topology. Uniform operator topology means point operator norm, that one, Tsj minus P, operator norm not converges to 0. If you remember the operator norm, you can consider the supremum of x over x is taken from the base k. It shouldn't converge to 0. Therefore, it has to, for every epsilon, we can find Sj. That value is bigger than or equal epsilon. Now, what we have, in this case, if we consider for each Sj, they are real numbers, you can find T and J, which is less than, take any element, any real number, Sj. You can consider any real number which is smaller than that Sj, and indices by T and J, and denote the Rj sequence. So if you take the Rj, what we found, Tsj minus Px, you can write Tsj, Tsj, Rj plus T and J. But we know that P is contraction, P is, go back, sorry. Wait. What was the P? I am on the wrong slide. Yes, here. P is a projection, and what satisfies TTP is equal to P for each T. Therefore, here I can write it. Px is PTRJX, and consider TRJ is an arbitrary element of Y. T and jy minus py. But we know from the tree, it converges, the item tree, it converges to 0. It converges to 0. That is the contradiction. It is bigger than or equal epsilon, but now it converges to 0. So our assumption, 1 is fails, is wrong, so 1 is correct. What we have now? If you take P is a rank 1 projection in this form, like, then the C0 semigroup is called uniformly asymptotically stable or uniformly ergodic. Both is correct. TT converges to projection P. Or weakly ergodic if the Dobryshin ergodicity coefficient converges to 0 as T goes to infinity. And for the rank 1 projection, we achieve that weakly ergodicity is equivalent to uniformly ergodicity, uniformly asymptotic stable of the C0 Markov semigroup on abstract state spaces. Also, it means that weakly ergodic, if and only if uniformly ergodic, if and only if for an arbitrary, take an arbitrary T0 and the operator TT0, and the Dobryshin ergodicity coefficient of TT0 is always less than 1. There exists a rho, it is in an element of the half open interval 0, 1, and that coefficient is less than rho. Okay, why do we need residuality also? We have spectrum. If you remember the spectrum, lambda I identity minus T not defined. And we have an arbitrary bounded operator, consider the spectrum. And the spectral radius also here, if you have a bounded operator, that, and if you consider the spectrum, that spectrum is a closed and bounded set, which is compact in complex plane. I need also just a few seconds to find also my mouse again. Now, spectrum is somewhere here, like. And it is in the unit, it is in the ball with the radius norm of T. Since T is bounded, you can define the operator norm. And the spectrum is in that ball. It is closed and bounded, it is compact or in the complex plane. And the spectral radius actually here is like the, take the all lambdas as a eigenvalue, let's say eigenvalue or the spectrum elements, and consider their modulus and take the supremum of the module of that lambdas. If I can show it here, look, like this one is our spectral radius of operator T. Now, and we know that the spectral radius is always equal to that value, or from the formula T to the norm of, the operator norm of the operator T to the power n to the power 1 over n, the limit value of that value is also equal to spectral radius of the operator T. Now, what we have here, if P is a Markov projection, T1 minus P, the spectral radius of T1 minus P is equal to Dobryshin ergodicity coefficient of the Tn. Tn here, the iteration of T1 n times. What I am talking about, it is that formula is also equal to T to the power n operator norm to the power 1 over n. The operator norm to the power 1 over n. Now we have a formula here. The spectral radius of T1 minus P is equal to the limit of the Dobrosch-Ergodicity coefficient in this form. If P is Markov projection, don't forget. Now what we have as a theorem, we have Markov projection. TT is C0 Markov semigroup, which is uniformly mean ergodic. Then the Dobrosch-Ergodicity coefficient is always equal to that exponential value, and is equal to that exponential value if and only if the spectral radius is equal to Dobrosch-Ergodicity coefficient. It is really important, that theorem, because first of all, let us have a look at the proof. If we have that equality, then from the formula, T1 spectral radius of T1 minus P is equal to that one. If you put on here, and if you consider the Tn minus P, which is the iteration of the Tn minus P, which is the iteration of the operator T1 n times, P is also projection. Therefore, I can consider in this form, and hence we have that formula directly. Tt minus P is always equal to Dobrosch-Ergodicity coefficient of Tt. On the other hand, if we have that equality, you can use the same equalities what we mentioned here. Then you get that the spectral radius of Tt minus P is equal to e to the power minus alpha, where is alpha the logarithm of spectral radius of T1 minus P. Then, basically what we want to say, if we have from C0 infinity to L of x, the continuous maps, what I defined as a C, here let's consider F. Take the value T and send to the operator, bounded operator Tt. Then, my question is now, is there any topological properties on that space? So we can put a metric in this form. If you look at here, what is rho m? Rho m means the difference of Tt minus St or Ft minus Gt. M is an fixed arbitrary real number, and your parameter T is an element of the closed interval 0m, and consider the supremum value of the operator norm for Ft and Gt. And find all that rho m, like here m is natural number, and consider the metric as follows here. It is complete metric space with the metric rho. Then what we have, this, if we have Markov C0 semigroups, here also is you can also here consider Ft and GTs are C0 semigroups and also Markov semigroups. Then if you have Markov semigroup, then that one itself is a metric, and the interesting things, that metric is equivalent to what we defined before, the metric rho. And the lemma shows that the Markov C0 semigroup collection is closed with respect to metric rho on the space of continuous maps from 0 infinity to L of x. And the last one, I guess I have one lemma, which is if we need also two collection. The first one is Markov operators, Markov C0 semigroups, which is commutative with the projection P, and they are also uniformly P ergodic, or the C0 semigroup, Markov C0 semigroups, which are invariant with the projection P, as follows here. And what we proved before, uniformly P ergodic C0 C0 semigroups is always invariant under the projection P. So that set, that collection is a subset of this collection. And what we have more, if P is Markov projection, if P is a Markov projection, then that subset is actually open in the set of the invariant Markov C0 semigroup collection. And there, the references basically depends on our articles with Faruk. And the last one is the main part of my talk. It is published in Annals of Functional Analysis this year. As I told you before, if you are interested in, you are welcome. It is my pleasure to discuss with you by email, or we can set a Zoom meeting and to discuss face-to-face from Zoom. Thank you very much.
Okay. Thank you very much, Professor, for the very enlightening talk and very engaging talk. I think that there should be many of our students interested in this topic. So next, we will now proceed with the Q&A session with our keynote speakers. So please free to raise your hand or type your question on the chat box, and I will direct them to our speakers. So you may raise your hand, please, if you have any question, or type your question on the chat box. Okay.
There is one question, I guess. For the Markov operator, you have to send a bounded operator is just from real function. Yes, regular. Regular. What do you mean regular linear operator? First of all, Irfan, I guess. Yeah. If you are, you mean that the linear operator, it is just an operator, even the operator need not to be bounded. For example, again, I lost. For example, take from C01 to C01 is a derivative operator. TF is F derivative, which is the domain is actually that operator is C1, differentiable function space. That operator is not bounded. First of all, is not bounded. Take F as a F of X is X to the power N, and consider the operator norm of F, which is the supremum value of norm of F is equal to 1, TF. And if you look at here, we are on the space on the set on the subset 0, 1. The norm is of course 1, because the norm on the continuous function space subnorm. And if you look at here, supremum n times x to the power n minus 1, which is equal to n. And if you take n bigger and bigger and bigger, then the operator norm blows up to infinity. So it is not even bounded. Therefore, first of all, you need a boundedness. And then you have one more property. The operator norm must be equal to 1. It means that it is isometry. You need one more things to take any elements from the base of the abstract state space and send to the base of the abstract state space. And for the textbook, if you write me an email, I will directly send to PDF file of the books and the pages where you can check and see.
Okay. Thank you, Professor, for
The video.
okay. Maybe we will proceed to the next question from Pak Jafaruddin.
Okay, thank you, Arfa. And thank you, Dr. Nasibe. It is a very interesting topic in pure mathematics. Although I don't understand all the explanation, I think it's just sometimes very difficult to me to understand all of this because this is not my background.
Yeah, sure.
But I think this is very interesting, and I try to understand that this is I try to connect with topology, but this is like a functional analysis. It is correct? Is it correct?
Yes,
Yeah.
right.
So this is a functional analysis, and actually we don't have the course, yeah, that connect with the functional analysis. Maybe you have suggestions about the basic lectures that we should give to our students, that so they can understand about the like this material, yeah, like the uniform ergosity of the Markov semi-groups. Maybe you have suggestion that about our basic lecture, maybe, or basic yeah, course.
Actually, if you want, maybe we can create an online course. It is my pleasure to give a lecture.
Oh, yeah. Okay, thank you. Yes, very good, very good.
Short course, or next semester, the next semester of the fall semester, if you want, we can create a real, like an online course every week, like 2 or 3 hours or 4 hours, 2 times a week. I don't know, depends on your and my time, but
Yeah.
I can somehow figure out, I guess, to create and to make a basically functional analysis online courses.
Okay, very good. Thank you very much. Yeah. Okay, very good. Thank you very much. Yes.
Let us discuss it. I am very happy to give because if you are interested in functional analysis, or even if you use norm space, you need to know the basic knowledge about the functional analysis part.
Yeah. Yes.
So, we have a must course, and I guess more than 8 years I am the lecturer for functional analysis. And
8 years.
for example, on Monday, but depends on time, please, 5 hours, don't forget the differences.
5 hours.
Like today, from 8 to 10 or 8 to 11, that means for you from 1 to 4.
Yeah, of course.
Online lecture.
Okay.
If you want.
Yeah, I think next year, in this next semester, we have a new curriculum for our university from our government. It means we also can make like a new course for our students. I think this is a good chance also for me to join online, yeah, by online with your course. Okay.
If your government gives a permission online, it is not correct, the legal means, but let's say legal, as a I am lecturer, and to give and grade their exams and to give them like a grade, that is it is my pleasure to give, but depends on your rule, government rule.
Okay. Thank you very much. Yes, I will discuss with our dean. Actually, we have a regulation about it, I think, and I hope in the new rule from the government also support it.
Hope so.
Okay, thank you.
Irfan, I am waiting your email. Please write me. I will send to you textbook.
All right.
Okay, thank you, Dr. Nazibe.
Thank you. See you. I stop to share my screen, I guess.
Okay.
Yeah.
So I think that there is no more question because there's no one raising the hand or also type the question in the chat box. So we come already to the end of this session. I would like to extend my heartfelt thanks to our distinguished keynote speakers, Associate Professor Dr. Nazife Erkusun Ozcan, for his invaluable sharing and very inspiring sharing. So your presentation have provided us with deep insight and new perspective on mathematics, especially on the functional analysis. So I would also thanks to all participants for your active engagement and thoughtful question. Your participation has made this event also success. And after this, there will be a token of appreciations. So I will hand over the session first to the moderator. And thank you very much for coming, Hocam. Teşekkür ederim.
Ben
And
teşekkür ederim.
and good evening. Good afternoon, Makassar time.
Thank you.
Okay, thank you. Thank you for the moderator. That was a very insightful session. Ladies and gentlemen, let me invite the head of mathematics department for the given of appreciation to our distinguished speakers. For Mr. Jafaruddin, PhD, the screen is yours.
Okay, thank you, Mutia. Yeah, we just waiting for the certificate, online certificate. Oh yeah, Dr. Nazife, actually we just maybe in these 3 years, we have new lecturers in our department, and most of them have planned to continue their study. So I hope that if we can accept like a scholarship from Indonesia, or maybe from Turkey, they can continue also to Turkey, some of them maybe. And I believe that some of them have a capability to continue to abroad. So I think this is also a good chance for them to follow this like international conference and know about you and another invited speaker, and they can connect you maybe for the to continue their study. Yeah, to abroad.
They want to do they want to make their PhD?
Yes, yes, yes.
I guess Arfa finished his PhD in Turkey, I think so.
Yeah,
no,
I graduated from
Thailand.
but right now I'm doing my PhD in Thailand.
Okay, how do you know Turkish? Or I understand because
Yeah,
you
teacher
pronounce
translated,
my name
uh,
my name correctly.
yeah, because I'm speaking Turkish fluently, Hocam.
Okay. So there is a program, Turkish scholarship for
Yes.
PhD students. They can apply them.
Yeah, yeah. I hope some of our lecturers and also our students, especially from our student from international class program, like Mutia. Now the MC now is Mutia, one of the students in international class program. I think we suggest them, we encourage them to continue to pursue their master or PhD abroad. Yeah, including in Turkey, I think. Yes.
They should do it.
Okay.
And also, I hope the MOU help.
Yes, yes. And the team of our university has sent the MOU. I hope you can get it about maybe 10 to 15 days.
Okay, it is
Okay.
okay.
Yes. Okay, Dr. Nazipe, this is a certificate from our university. Thank you very much for the very good presentation. I think your knowledge, your sharing knowledge inspire us and also encourage us to more know deeply about mathematics, especially pure mathematics. Thank you very much to Dr. Nazipe. And thank you also for you recommend your student to become a presenter here.
Yes.
And actually I have discussed with the committee that because the different the time of different about 5 hours from Indonesia and Turkey, so we just discussed to allocate the time for your student to after Professor Gultub. Yeah, I'm sorry, my pronunciation of the name of Turkish is not correct. Okay. Okay, thank you very much, Dr. Nazife. I believe that in the future, you will come here in Indonesia based on our program that we have discussed before. And I believe also Ion, maybe some staff also can go to Turkey. Thank you very much,
Also,
Dr.
you're
Nazife.
welcome. Take
Yes.
care.
Okay, thank you. Now we will start the third keynote speaker session. The third session of the conference will be moderating by Mr. Arfa MSc as the moderator. He is lecturer from the Mathematics Department, Faculty of Mathematics and Natural Sciences, Universitas Negeri Makassar. In this session, we will have outstanding academics and keynote speaker, Association for Prof. Gultub from Turkey. So I would like to hand over the session to the moderator.
Okay, thanks to the moderator for handing over the session again to me. I'd like to say good afternoon to everyone and good morning for Associate Professor Gultu Hocam. Merhaba, hoş geldiniz hocam.
Merhaba Arfa, good morning.
Okay, nice to
How
see
are
you.
you? Happy to see you again.
Yeah, it's been a long time not to see you, and finally we can meet in this international conference. So
Yes.
we are honored to welcome you to our international conference, and we are really to listen on your thoughtful sharing for today. So before we begin, I'd like also to say thank you to our organizing committee for organizing this international conference. Especially for me, I'm really happy for inviting the keynote speakers, my advisor when I did my master program in Carolina Technical University. I'm working with her for 3 years, working together on geometry, specialized in on like hypersurface and also the manifold. And I think that what I've learned from there was very inspiring to do a lot of research and also deeper on geometry. Well, so to maximize our time together, we will begin our session with our keynote speaker delivering his research on our filter room. And following that, we will recon to the Q&A session. So let me introduce our esteemed keynote speaker first. So Associate Professor Gultu is a faculty member of the Mathematics Department, Faculty of Science, Karolinska Technical University, Trabzon, Turkey. He specialized on mathematical and computational biology and also in mathematical physics and geometry, specialized on differential geometry and manifold. Beside that, she already published a lot of articles on international reputed journals. The last one that the article that we're working together on the light hypersurface. And without further ado, please join me welcoming our keynote speaker, Associate Professor Gultu, and the time is yours.
Okay, thank you, Arfa. And I would like to start by thanking the organizers for inviting me. And I would like to say that I am proud of the success of Arfa during his studies in my university. And everyone in my department remembers you.
Thank you.
Yes, if you want to come again, of course we can make new resources with you. And I can share my screen. Today I will talk about manifolds theory, actually the fundamentals of manifolds, because this is a very deep topic in the pure mathematics. The Euclidean space Rn is the prototype of all manifolds. It is not only the simplest, but locally every manifold looks like Rn. Actually, a manifold is a generalization of curves and surfaces to higher dimensions. I will define the topological manifold, but first we recall three definitions from point set topology. In topology, a second countable space, also called a completely separable space, is a topological space whose topology has a countable base. We mean a topological space is second countable if there exists some countable collection U of the open sets Ui, such that any of them can be written as a union of subfamily of U. Another definition is the topological space is locally Euclidean. If every point P in M has a neighborhood U such that there is a homeomorphism phi from U onto an open subset of Rn, we call the pair U and phi as a chart. U is a coordinate neighborhood and phi is a coordinate map. A Hausdorff space is a topological space in which, for any two distinct points, their neighborhoods are disjoint. We can find open sets U and V such that their intersection is empty. A topological manifold is Hausdorff, second countable, and locally Euclidean space. And it is said to be of dimension n if it is locally Euclidean of dimension n. We mean the topological manifold is of dimension n if this homeomorphisms from the open sets to the subsets of Rn. And we give an example. Euclidean space Rn itself is a topological manifold because it's covered by a single chart with the identity map on it. This is a homeomorphism. And also every open subset of Rn is a topological manifold. Another example is the graph of y equals x to 2 over 3. This is a curve actually, and it is a topological manifold too. Here the homeomorphism is defined by the map which sends each point to its first coordinate. However, across this is the first curve and this is the cross, is not a topological manifold because we cannot find a homeomorphism from the open subsets of cross to a subset of Rn. Any two charts on a topological manifold are said to be C infinity compatible if the following two composition maps, we say transition functions, are differentiable. These two maps are called transition functions between the charts. And if the intersection of U and V is empty, then the two charts are automatically C infinity compatible. And this diagram shows two open sets covering M and the charts a C-infinity atlas on a local Euclidean space M is a collection of the charts and they are pairwise C-infinity compatible charts covering M. An atlas on a local Euclidean space is said to be maximal if it is not contained in a larger atlas. A smooth manifold or differentiable manifold is a topological manifold M together with a maximal C-infinity atlas. So it is a differentiable structure on M. Here we give some examples of smooth manifolds. Any open subset of a manifold is also a manifold and smooth manifold. Here we take the charts as the open subsets covering M intersection with the open subsets of V and the restriction of the phi, the homeomorphism. Another example is the graph of a C-infinity function f from a subset of Rn to Rm. This graph set is a smooth manifold with the together with the homeomorphism phi. Actually, this is the projection map, and also its inverse is a homeomorphism. And this shows that many of the familiar surfaces of calculus, for example, an elliptic paraboloid or a hyperbolic paraboloid, are smooth manifolds. And we can give, as a simple example, the unit circle. And we describe a C-infinity atlas with 4 charts on it. The charts are the upper and lower semicircles, U1 and U2, and the right and left semicircles, U3 and U4. We choose them because we can cover the unit circle with these sets. And on U1 and U2, we take the coordinate function x as a homeomorphism onto the open interval -1, 1. Similarly, we can make it for the U3 and U4 in the y-axis. And it is easy to check that every non-empty pairwise intersection of these open sets, we can define a transition function.
Recording in progress.
Phi beta circle phi alpha inverse. For example, on the intersection of U3 and U1, the transition function is this. And they are C-infinity. So this is a maximal atlas for the unit circle. On a manifold, if U alpha, phi alpha, and Vi, psi I are C-infinity atlases for the manifolds M and N, then we can construct the product manifold by taking the products of the charts and the homeomorphisms. And the dimension is m plus n. For example, the cylinder and the torus are product manifolds. We can make this product infinitely many times. Thus, the n-dimensional torus is also a smooth manifold. We define a diffeomorphism as a bijective C infinity map whose inverse is also C infinity. I would like to talk about tangent spaces on a manifold. The tangent space at a point on a manifold is a vector space that captures the possible directions in which one can move from that point. And we can locally approximate the manifold structure near this point. More formally, if M is a smooth manifold, the tangent space TPM is the set of all the tangent vectors at P. And this diagram shows the tangent plane on a surface. Here we have a curve passing through the point X on a manifold. And we have the tangent to that curve, the vector V, but we can make it infinitely times this. We have a collection of the tangent vectors. So the plane involving these vectors is called the tangent plane on a manifold. And a tangent vector actually defined by this function V from the set of all the differentiable functions on M to R, and it is R linear and satisfies the Leibniz condition. And with the addition and scalar multiplication, the set TPM is a vector space. Now let's see the coordinate system in the manifold M, and we can define the derivative of a function f by the help of the natural coordinates of Rn. And we can say that these partial I vectors are tangent vectors to M at the point P, and actually they construct a basis for the tangent plane on M. And we can write a tangent vector by the composition of these partial I vectors. Vi is the components. Vi are the components of the tangent vector V. Every tangent vector in TPM can be written by this. And a vector field V on a manifold M is a function that assigns to each point a tangent vector. And Vf denotes the directional derivative on M. We take the directional derivative of f in the direction of the tangent vector at P. And we can make it for every point on a manifold. And this diagram shows a parallel vector field on a manifold along a closed path. This vector field is parallel throughout this path. We say that a vector field is smooth if Vf is smooth for all functions. And also vector fields can be added together or multiplied by a function. So the set of all the vector fields is a vector space. We show it by Ic-Camm. And we can express a vector field by the composition of the partial I vectors. Another definition is the bracket operator. We define the bracket operator of two vector fields by this. It is also called the Lie derivative of vector fields, and it measures how much the flows of V and W twist or mix with respect to each other. And the bracket assigns to each point on a manifold the tangent vector this, defined by this equation. And it has following properties: R bilinearity, skew symmetry, and Jacobi identity. And this is a very useful tool in the theory of manifolds. We define a function between two manifolds n and m, and it is a C infinity map. At each point, f induces a linear map f star from the tangent space of n to the tangent space of m at the corresponding points p and fp. This is called the derivative function or derivative map, and it is defined by a directional derivative again. Now we can talk about the submanifolds. Roughly speaking, a submanifold of a smooth manifold is a subset of M that acquires its manifold structure from M. In particular, P need to be a topological subspace of M, so it has the induced topology. By the induced topology, we mean if X2 is a topological space and A is a subset of X, this is the tau A induced topology, and defined by the intersections of the subsets in X and the set A. And these are open sets too. A manifold P is a submanifold provided P is a topological subspace and the inclusion map defined by I is a smooth and its differential map is injective at each point. For example, the coordinate systems produce submanifolds we take Z equals 1 plane, and it is diffeomorphic to R2 with this map. We define an immersion phi as a map from one manifold to another manifold. It is a smooth mapping such that its differential map is injective for all P. Every regular curve is an immersion. By the regular, we mean the velocity never zero. Also, we define an embedding of a manifold, submanifold P into M. It is an injective immersion phi, such that the induced map is a homeomorphism onto the subspace phi P. The standard example is the mapping from Rm to Rn. It is something like we are extending the coordinates of the points to the dimension n. Actually, locally, every immersion looks like this. As an example, we take the curve alpha. This map self-intersects. Its graph is a figure 8 shape, but its derivative is still injective at every point, so it is an immersion. But it is not an embedding, since it is not the immersion is not injective. The derivative function is injective, but immersion itself not injective. Some manifolds and embeddings are very closely related. If P is a submanifold, then the inclusion map is an embedding. Conversely, if phi is an embedding, then the image of P under phi is a submanifold. A submersion psi is a smooth mapping from the manifold M to B that the derivative function is surjective. Submersion is a smooth map between smooth manifolds that locally looks like a projection onto a lower dimensional space. Here the lower dimensional space is B. For example, we take this projection from R3 to R2, and this is a submersion because the derivative has rank 2, so surjective. And I will give a brief information about the semi-Riemannian manifolds. Actually, this fundamental topic formalized by Albert Einstein through the theory of special relativity. He says light propagates at a constant speed in all directions and for all observers, regardless of their state of motion. A decade later, Einstein expanded his framework to the general theory of relativity. In both physics and mathematics, Minkowski space constitutes the mathematical framework in which the principles of special relativity. Minkowski space unifies space and time into a four-dimensional manifold. The universe, a according to general relativity, is modeled as a smooth manifold. The fabric of spacetime is shaped by the presence of mass and energy. The curvature of a manifold is precisely captured by the pseudo-Riemannian metric. This metric allows us to measure distances and times in a curved spacetime. Unlike in flat space, where we can easily use the Euclidean geometry to measure the distances, in a curved spacetime, the distances between 2 points depend on the curvature of the manifold. So the gravity is the effect of spacetime itself curving in response to mass and energy. And this geometric framework has allowed scientists to predict phenomena such as gravitational waves, black holes, and the expansion of the universe. Also, it is not only the language of general relativity, but also it bridges the gap to more advanced topics in physics such as string theory and quantum gravity. We need to define a symmetric bilinear form. If V is a real vector space, a bilinear form on V is defined by B, and a symmetric bilinear form B is called positive definite if this condition holds for every vector V, or positive semi-definite if this condition holds for every V. Non-degenerate if for all W, if BVW equals 0 implies V is 0. If B is a symmetric bilinear form on V, then for any subspace W of V, the restriction is also a symmetric bilinear form. And the notion of index. The index of a symmetric bilinear form is the largest integer that is the dimension of a subspace W in V, on which the restriction of B is negative definite. So we can define a metric tensor on a smooth manifold. It is a non-degenerate symmetric bilinear form of constant index. And if we define a metric tensor on a smooth manifold, then we call it a semi-Riemannian manifold. We can say if the index is 0, this is the Riemannian case. G is the Riemannian metric and the M is a Riemannian manifold. If the index is 1 and the dimension is greater than 2, then it is called a Lorentzian manifold. If x1 and xn is a coordinate system on the manifold M, the components of the metric tensor G are defined by this. Here we show by these parentheses the standard inner product actually, but the semi-Riemannian case. We know that this partial I and partial J are the basis vectors on the tangent space. And for any vector fields, their inner product is defined by this. Since the metric is non-degenerate, at each point of P, the matrix of G is invertible. This is the standard inner product, Euclidean sense, and this is the semi-Riemannian inner product. We take first V terms in this equation as minus signs in front of them. So the index is V. Any tangent vector in a semi-Riemannian manifold has three causal characters. We say that V is space-like if the inner product of V by itself is positive or V is 0. We say null or light-like if the inner product is 0. We say time-like if the inner product is negative. In the Riemannian case, we only have these space-like vectors because the metric is positive definite. The category into which a given tangent vector falls is called its causal character. This terminology derives from the relativity theory. In the Minkowski spacetime R1n, here we take the index 1. It means we have only one minus sign. The light cone is defined by this equation. It means we have only light-like vectors on a light cone. This is the light cone. And in a light cone we have time-like vectors. Outside of the light cone we have space-like vectors. On the light cone we have light-like vectors. And also there are causal characters of curves in the R1n, the Minkowski space. And the causal characters defined by the inner product of the velocity vector by itself. If this inner product is negative, the curve is time-like. And if inner product is 0, the curve itself is a light-like curve and the space-like curve. One curve can be partly space-like. I mean, at some points on the curve, we have space-like case or time-like case. It can be a mix of them. And the curve, a time-like curve, represent the trajectory of a massive particle in the physical sense, and the light-like curve represent the trajectories of massless particles like photons, and the space-like curve represents a path moving faster than light. To define the derivation on a manifold, we give a Levi-Civita connection. If V and W are vector fields on the semi-Riemannian manifold RVN, The derivative of a vector field along another vector field is called a connection and defined by this equation, and we can call it covariant derivative. A connection D on a smooth manifold is a function from the product of the vector space of vector fields to the vector space of vector fields. So the VW is linear, R linear, and satisfies this derivative formula. If these three conditions hold, then we call it a linear connection on M. On a semi-Riemannian manifold, there is a unique connection D such that these two conditions hold. This is the Lie derivative, and this condition called the metric compatibility. So D is a Levi-Civita connection. And we can compute the components of the Levi-Civita connection by Christoffel symbols shown as gamma. Gamma is symmetric, and we compute them by this equation here. Jm, Gim, and Gij are the metric components, and G to Km is the inverse matrix of the metric G. For example, the Levi-Civita connection of the semi-Euclidean space RVN has 0 components. This is the metric coefficients. They're -1 or +1. In the Riemannian case, all the metric coefficients are +1. And the connection coefficients are 0 everywhere, and it indicates we have a flat space. And I will give a brief introduction to light-like hypersurfaces. Let M bar be a M plus n-dimensional semi-Riemannian manifold, and G is the metric with constant index on M bar. When M is a m-dimensional submanifold in M bar, we consider a subspace. This is a normal subspace of M. In the Riemannian case, the normal space is orthogonal space to the tangent space. Here we define the normal space by the vectors orthogonal to the tangent vectors. We can define a distribution on a manifold A distribution D assigns to any point a vector subspace dx in the tangent space at x. So we define a radical distribution on a manifold, submanifold M by rad TPM. This is the intersection of the tangent space and the normal space, and it is non-empty. In the Riemannian case, this intersection must be empty, but in the semi-Riemannian case, it can be different from the empty. If the rank of a radical distribution is R, then M is called a R-like submanifold. And in this case, we have R linearly independent light-like vectors in the radical space. If R is 1, I mean, if we have only one light-like vector in the radical distribution, it is called a light-like hypersurface. The complement vector bundle, here maybe I can explain the vector bundle. If we take the union of tangent spaces at every point on a manifold, then we have a tangent bundle, and it is also a manifold. So we mean at every point P, the union of the radical distributions by the radical vector bundle. The complement vector bundle to the radical is a screen vector bundle, STM. We have only light-like vectors on the radical, but the non-light-like vectors included in the screen bundle. So screen bundle is non-degenerate. We define these bundles for separating the tangent space of M into two orthogonal subspaces. Tm can be written as the orthogonal direct sum of radical and screen distributions. And we need to know the definition of transversality. Two submanifolds L and M of a manifold N are transversal at a point X in the intersection of L and M if the tangent spaces TXL, TXL, and TXM are they generate TXN. So they're called transversal. And on a submanifold M, this is the screen bundle, and this is the complementary bundle to the screen bundle. It's the R light-like submanifold. If we take R as 1, this is the light-like hypersurface case. We have a coordinate neighborhood of M is U, and set of psi I is a basis of radical distribution. So C are light-like vectors. If we have light-like vectors, then there exist other light-like vectors which are linearly independent of Xi. Ni, other light-like vectors, we have R light-like independent vectors in the submanifold case, but in the hypersurface, light-like hypersurface case, we have only one Xi and one N. The set of all these vectors N is called the light-like transversal vector bundle and shown by LTR-TM spanned by the vectors N. These N vectors must be defined because if you have a light-like vector in a basis, you have automatically another light-like vector linearly independent of it. Also, in the outside manifold M bar, we have this decomposition. We can decompose its tangent space by the help of the tangent space of the submanifold M and the transversal vector bundle of M. In the Riemannian case, instead of TRTM, we have the normal space, but in the light-like case, we cannot do it because TM and the normal space has a intersection. So we have a quasi-orthonormal basis for M bar along the submanifold M. It is Xi, N, X, and W vectors. Here Xi are in the radical distribution, N are in the light-like transversal vector bundle, X are in the screen distribution, and W are in the complementary bundle to the screen bundle. In the light-like hypersurface case, we have this quasi-orthonormal basis because we have in the radical bundle only one light-like vector. So we have in the transversal bundle only one light-like vector, and these are the screen bundle bases. And we can write the Gauss-Weingarten equations for a light-like hypersurface too. Here, nabla is the Levi-Civita connection on M. And by this, we can define a Weingarten operator A and the second fundamental form H on a light-like submanifold M. The second fundamental form of a surface is a mathematical formula that measures the bending properties of the surface in relation to its normal. So it provides information about the curvature. The shape operator helps us understand the change of the surface's normal direction at each point, and it is in a relation with the second fundamental form. I want to show you some examples from my published paper. This is a paper about the null scrolls along a light-like submanifold. Null scrolls are the null scrolls correspond to the ruled surfaces in the Euclidean case. Here we have some examples. This alpha is a light-like curve. This is the graph of alpha. This is a null curve because its velocity is a null vector, and we use Cartan frame on a null curve instead of the Frene frame for simplicity. And this is the null scroll defined along this curve. In R25, we have a light-like submanifold defined by these coordinate functions, and the radical is defined by C1, C2. Here we find the C1 and C2 vectors, and the screen bundle is spanned by W1 and W2 vectors. They are space-like vectors. And the light-like transversal bundle is spanned by N1 and N2. Another example is in the R4 14. Yes. Yes, Arfa.
Yeah. I think that our time for the presentation will be up, and we'll proceed to the Q&A session. Hocam,
Okay.
this is
Maybe I can stop the screen sharing. Okay.
Oh, okay. So thank you very much, Hocam, for a very uh great presentation as a basic or the foundation for learning about the manifold and differential geometry. I really remember this course was quite hard at the first year, but yes, finally we can struggle for that. And I will open the Q&A sessions for our keynote speaker. So feel
Okay.
free to raise your hand or type your question in the chat box, and I will direct them to our speaker. I think that there is one question on the chat box. It's from Mariani. The question is, can we approach all the properties on manifold to the geometric properties on the Cartesian space Rn?
Can we approach all the properties on manifolds to the geometric properties on the Cartesian space Rn? If it is a manifold defined in Rn, of course we can, but there are some other manifolds, for example complex manifolds. So in that kind of manifolds we cannot do it.
Some property can be extended to, can be approached by the geometry on the Rn, and some of them are not. It depends on the type of manifold itself. Okay. If there are any more questions, you may raise your hand, please. And then um, typing the question in the chat box. Okay, from Muhammad Zakir Asikin, please, the time is yours.
Oh yes, thank you, moderator. So, I just want to ask you some simple question, simple question about the uh, manifolds in semi-Riemannian. So you just said that this semi-Riemannian is about to count some structure of spacetime in general relativity. So why we cannot say that the Riemannian manifold is to count it? Why you say that it's just for the semi-Riemannian? So, and maybe you can just answer like the theoretical, because of for honestly I cannot just some of words and symbols I understand from what you just said, Miss. Maybe just that I can ask.
Thank you.
Actually, I don't understand the question.
Okay. I would like to clarify it, maybe. Like,
Uh-huh.
for, I think that the question will be like this. So we use the semi-Riemannian manifold to approach the theory of general relativity.
Yes,
Instead of the Riemannian manifold, why we shoot the semi-Riemannian property, not the
yes,
Riemannian property, so for approaching the general theory of general relativity.
because we need to define the time dimension, and it is achieved by defining the minus signs in the Riemannian inner product. So this is a physical question in the field of physics. So for further information, we need to know the basics of the physics of the general relativity. But in the mathematical sense, it corresponds to the time dimension, because we we need not only this the vectors in space, we also need like or light like they also define the future or past pointing vectors to understand the relativity theory. But as I said, this is the physics question.
So there will be a connection to the physical, to the physics theory. I think, just to clarify that, it depends. I mean, it is like the theory proposed by the Albert Einstein actually. So there will be
Yes.
one dimension that is time. Instead of the space, we have a dimension of time, which is in the space of the light itself. That's why we approach the same meaning.
Yes, yeah, one needs to understand the fundamentals of general relativity. We only introduce the mathematical framework.
Yeah. Okay. There is one more question, Hojam, and this is maybe the last question for our session. The question would be, like, what is the role of the tangent space in the context of topology? And then how maybe just like how we understand about this tangent space as a beginner or in studying about the topology.
Tangent space. Tangent space is tangent space provides us to approximate, for example, a surface on a surface at a point. We have a tangent space, so we can understand the shape of the surface at that point. Like the curve case. On a curve, V has a tangent vector, the velocity, so we can understand the shape of the curve as this. On a manifold, on a surface, we need to understand its tangent space at a point to understand the shape of the surface. So I can say that it is not topological, it is differential geometry. It is defined for understand the shapes.
Thank you, Hajam. So we use to clarify, we use the tangent space to identify or investigate the the property like the surface and the form of the surface itself. Okay, so I think that's all for we are now in the end of the session already. So I would like to extend my heartfelt thanks to our keynote speaker, Associate Professor Gultu, for her invaluable sharing. And I think that your presentation provided us a basic things, especially on the differential geometry and manifold. And hopefully that your sharing will be beneficial for us to learn further about geometry. And I also would like to thanks to all participants for your active engagement and your participation. And of course, it make our session live and also success. We hope that today's sharing from our three keynote speakers inspire us for our further research and for our further study. And I'd like to say again, thank you for your sharing, Hojam, and thank you for coming to our international conference. Hopefully that there will be another session for inviting you or collaborate with you again. And I'd like to hand
Thank you
over.
for listening.
Yeah, thank you, Hojam. And I would like to hand over the session back to the moderator.
Okay. Have a nice day.
Sorry, Hojam, there will be a token of appreciation, maybe. So we would like to invite you to the token of appreciation to give the certificate and some speech from our department staffs.
Okay.
Okay, thank you. Next, I will hand it back to Mr. Jafarudin, PhD, to hand over the certificate to the speaker. For Mr. Jafarudin, PhD, the screen is yours.
Okay, thank you, Moderator Arfa, and also MC. And thank you very much, Dr. Gultub, for your presentation. It was a very interesting topic, and you know that some of the participants of this conference also know is have a course about the introduction of topology. So actually, I think they are very interesting about the topic that you have delivered today. So I think this is a very good chance for them. They can get more knowledge from another scholar from Turkey. And I hope in the future, Dr. Gultub, maybe this is also my hope to my friend, Dr. Nasibe, that maybe some of our students and also some of lecturers also can follow the footsteps of Arfa and also can learn in Turkey, maybe in your university or Dr. Nazibe's university. Okay, and this is a certificate. Okay, hello, certificate. Oh yeah, please. Okay.
Can you hear me?
Yes, yes. And this is a certificate of appreciation for you. Yes, and for the.
I would be happy to study with your students in my university. We are always open to new researches.
Oh yes. Okay. We hope that um, our student and also some lecturer also can continue they pursue their doctoral or master degree in your university or
Yes.
in Turkey. Yeah.
Yes, of course.
Yeah, and for your information, I think you already know that we have like international class program, and now we find change to collaboration for our university and to another university around the world, and also we also already make a collaboration with the HTTP University, and we also have that your university also maybe we can make like a memorandum of understanding MOU. So I hope that Alpha
Of course,
as a young lecturer in our department also can facilitate for this collaboration. So we find more collaboration in another country. Okay, thank you very much, Professor, Dr. Associate Professor Gulto, for your very insightful and interesting presentation. I think some of us may be confused about the material, but it is encourage us to understand more about the pure mathematics. Thank you very much.
thank you too.
Okay, thank you. And for the last session of the day, I hand it back to Mr. Arfa MST as the moderator to continue to the speaker SG Head Eriksal from Turkey. Time is yours.
Okay. Check. Okay. Thank you very much for hand offering the session again to me. And before I started, I'd like to say good morning for our next speaker, that is Miss Ezgi Har Yüksel from from the Hacettepe University. So we would like to welcome you to our international conference. And before we begin, I would like also again to say thank you to the committee for organizing this session for our next speaker. So to maximize our time for this session, we will begin with the speech from our keynote speakers, and after that following by some Q&A sessions. So let me introduce first for a brief about our next keynote speakers. So Ms. Ezgihan Erkusul is a research assistant in Ankara Medipol University, but right now she's also doing a PhD in the mathematics department, Faculty of Science, Hacettepe University, under the supervision of the Associate Professor Dr. Nazife Erkusul Ozcan. I think that she's also sharing the same research interest with Professor Nazifa before. So without further ado, please join me in welcoming our next keynote speaker, Ms. Ezgi Han Eryuksel. And the time is yours.
Okay, thank you. I am sharing my screen. Mhm. Okay, hello everyone and welcome. I apologize for my camera not working. I'm sorry. I am pleased to have this conversation with you today. First of all, let me introduce myself. My name is Ezgi. I am PhD student at Hacettepe University and research assistant at Ankara Medipol University. Today, I will be giving a talk about demi-AB continuous operators. This talk contains several main four parts. In first part, I will define the basic definitions. In the second part, I will discuss the various notations of convergency. These included order convergency, relatively uniform convergency, unbounded order convergency, unbounded norm convergency, and unbounded absolutely weak convergency. In the following section, I will present the definition of AB continuous operators, and in the final part, I will introduce the definition of demi-AB continuous operator and talk about some of its properties. A real vector space E is said to be an ordered vector space whenever it is occupied with order relation smaller than or equal that it is closed under addition and scalar multiplication. A real space is an ordered vector space with additional property. The supremum or infimum of any two elements exists and belong to the set. Let's be a norm on real space. If absolutely of x smaller than or equal absolutely of y implies norm of x smaller than or equal norm of y, then the norm is called lattice norm. And the space occupied with lattice norm is called normed real space. If the normed space is completed with respect to given norm, it is called a Banach lattice. For example, the spaces LP with P norm are Banach lattices. Another example, K is compact and Hausdorff space. The continuous function on K with subnorm is a Banach lattice, but the space with P norm is a normed real space. Another definition, a normed real space is said to be order continuous whenever the net x alpha is decreasing and the infimum is 0, implies norm of the x alpha is decreasing and the infimum is 0. In this definition, the sequence instead of the net, it is called sigma order continuous normed real space. For example, P is between 1 and infinity. The space LP is Banach lattice with an order continuous norm. On the other hand, the space, the continuous function, the closed interval 0, 1 and L infinity with occupied with subnorm are Banach lattice, but they do not have an order continuous norm. A vector in a real space is called an atom if two elements taken from the closed interval 0e have infimum equal to 0, imply either is equal to 0 or y is equal to 0. For example, in the space R2 occupied with pointwise order, the vector 1, 0 is atom. And the last definition, A is set of all discrete and atoms. A real space E is called an atomic real space if the band generated by the set A is equal to entire space E. For example, R2 is an atomic real space. Okay, I am continue definition of convergency. First convergency, order convergency. A net x alpha in a vector lattice is said to be order convergent if there exists another net y beta. Y beta is decreasing and the infimum is 0. For any beta, there exists alpha 0 such that absolutely of x alpha minus x smaller than or equal y beta. Another convergency, in a real space, a sequence xn, an element, positive element u. the sequence Xn is said to be relatively uniformly convergent if there exists a sequence of positive scalar epsilon n with epsilon n is decreasing, the infimum is 0, such that absolutely of xn minus x smaller than or equal epsilon and u. Relationship between order and relatively uniform convergence. We can say that relatively uniform convergence implies order convergence, but it is the convergence it is not true. For example, on the space the continuous function closed interval 0, 1, we can say that relatively uniformly convergence is equivalent to uniformly convergence, and order convergence implies pointwise convergence. Consider the sequence of function fn, choose this, and the function fx is defined this way. Fn pointwise convergence to fx, but Fn does not convergence to uniformly fx. Let A be a real space. X alpha is said to be unbounded order convergent for every positive element u. The infimum of absolutely of x alpha minus x and u order converge to 0. Relation between order and unbounded order convergence. We can say that order convergence implies unbounded order convergence. The converse of this statement, it is not true. For example, consider the standard basis in the space C0. Standard basis unbounded order converge to 0, but it is not order converge to 0. Let A be a Banach lattice. The net X alpha unbounded norm convergent for every positive element u, the infimum of the absolutely of x alpha minus x and u norm converge to 0. For example, in the space C0, unbounded norm convergence is equivalent to coordinate-wise convergence. And the last convergence, let A be a Banach lattice. The net X alpha is said to be unbounded absolutely weakly convergence. For every positive element u, the infimum of absolutely of x alpha minus x and u weakly converge to 0. We know that norm convergence implies weakly convergence. Thus, we can say that unbounded norm convergence implies unbounded absolutely weak convergence. However, the converse is not true. For example, in the space L infinity, consider the standard basis. En, you are convergent to 0, but the sequence does not unbounded norm converge to 0. We will define AB continuous operator. Let A be a Banach lattice. An operator T is said to be A to B continuous operator if for every positive net X alpha, whenever X alpha A converge to 0 implies X alpha B converge to 0. The class of all the A to B continuous operator denoted by N this. Okay. Let A be a Banach lattice. An operator T is said to be demi-AB continuous operator denoted by this for every positive X alpha net. Whenever X alpha A converge to 0 and X alpha minus X alpha B converge to 0 imply X alpha B converge to 0. The class of all demi-AB continuous operator is denoted by this. For example, let A be a Banach lattice for every beta real number, but beta is not equal to 1. The operator beta identity is demi-AB continuous operator. Let us now examine the relationship between AB continuous operator and demi-AB continuous operator. Every AB continuous operator is demi-AB continuous operator, but the converse is not true. For example, the space C0 choose Ic-Camm standard basis. The sequence is UO converge to 0 in the space, but it is not order converge to space in the space. Thus, beta identity operator is demi UOO continuous operator, but beta identity operator is not UOO continuous operator. They are equivalent only in some special case. The theorem, the space is finite dimensional Banach lattice if and only if sigma UOO continuous operator is equivalent to sigma demi UOO continuous operator. Another theorem, let A be a Banach lattice with order continuous if UNUO continuous operator is equivalent to demi UNUO continuous operator, and then the space is atomic. Let A be a Banach lattice. T is an AB continuous operator and S is demi-AB continuous operator. The sum of the operator is demi-AB continuous operator. It is important to observe that the sum of the two demi-AB continuous operator did not be demi-AB continuous operator. For example, choose beta is equivalent to 1 divided by 2. We can say that 1 divided by 2 identity operator is demi-AB continuous operator, but sum of the operator is equivalent to identity operator, and identity operator is not demi-AB continuous operator. Therefore, demi-AB continuous operator is not a vector space. Thank you for listening.
Okay. Thank you for thank you for Ms. Esgihan for the insightful and engaging presentation. I think your expertise on this operator has provided us a new information for us, and I'm sure that the audience has much to reflect on. So at this point, we will now open the Q&A session. So to all participants, if you have a question, please raise your hand or type your question on the chat box. We will facilitate and proceed the question to our speaker. Okay, maybe I have a question. Maybe I'm interested in this talk actually. As right now I'm also working on some operator theory on the functional analysis. We're working on operator that what we call as resolvent mapping, and I found that there is an operator here on the Banach lattice. So is there any what is the Banach lattice function what is the main purpose of the Banach lattice operator actually? Like, let's say, for example, that what I'm working right now is the resolvent operators. In resolvent operators, we try to find the minimizer of any function on the geodesic space or in Banach space. So for the lattice, demi-AB,
Continuous operator.
Yes, the operator itself that you are talking about, is there any specific function or is there any specific goal of this operator in the Banach space, or what the function of this operator is actually?
Ezgi, may I explain if you allow me?
Lütfen hocam.
Okay. Probably she is a bit nervous, and so maybe I could explain more. But first of all, the motivation of the definition of demi-compact operator is to study for the fixed elements, fixed points at the beginning, at the 1960s, sorry. And then she defined a lot of convergency, UOUN, but for such convergence, we need a lattice operation on the normal space. In your case, you have only Banach space, you have norm, even you don't have any order on the space. But if you consider any classical functional analysis examples of the Banach space, LP, C01, small LP, all of them are actually Banach lattice. You can put on order and you can put also lattice operations, supo and inf. And then that was the main motivation for us to use such very active and popular topic convergence on function on Banach lattices and define an operator intuitively from demi-compact operators. And therefore, we really need, at least for the beginning of the PhD, Banach lattices. We can also consider only just the ordered Banach space. In any case, we always need order. But in your resolvent operators, you have Banach space, and you have an operator which satisfies some properties, and you are looking for, I don't know exactly, but the minimality of the functions, what you said.
We try to find the fixed point of the function, where the fixed point of the function itself is the minimizer of the function. So we have like some iteration by using the operators to approach the fixed point of any function in the Banach space.
Okay, for the demi-compactness at the beginning, but the story starts from demi-compact operator case. Ezgi, do you have references in your slides?
No,
Reference slide'da.
yok hocam eklememişim.
Could you please open your paper if possible? Makaleni açar mısın lütfen?
Açayım hocam.
Let us go to references. Arfan, you can check which one, where is the 16 Patrician construction of fixed points of demi-compact mapping on Hilbert space. Maybe you can, because it is very interesting. Why it is interesting? If you look at the guy, is it here? No. Please write, also email to me. I will send some documents to you. There is a professor from Tunisia. He is very interested in the demi-compactness and Fredholm operators and their spectral properties, which is, I guess, closest to your area. I think so. I don't know, but you can read. If it is close, it could be helpful for you.
Yes, thank you, John. Because right now I'm actually trying to find out some application of my functional analysis. I mean, the function that I'm working right now. So maybe I think that there is like a possibility to apply this mapping as well to to enrich our research. So I strongly believe that there will be a connection between my work and also this one. So I'm really interested to find it out further later on.
Okay, please write an email and we can continue discuss by Zoom. And also send to you that paper, and I will send some professor names to check their papers about Fredon operators.
Teşekkür ederim hocam.
Rica ederim.
Okay, is there any else question from the participant? Please raise your hand, or you may type your question on the chat box, please. Okay, I think there is no more question. So once again, let's give a round of applause to our speaker for the thoughtful presentation, and also for the response for the questions today. So I also again thank you to all participants for keep staying on our international conference, keep active on the discussion process, and I believe that all the participants make our international conference today successful. And once more, I will return again this session to the moderators. So thank you very much, and see you again on the next international conference.
Okay, thank you. Next, I will hand it back to Mr. Jafaruddin, PhD, to hand over the certificate to the presenter. From Mr. Jafaruddin, PhD, the screen is yours.
Okay, thank you, Mutia and also Arfa. Yeah, and also I'm sorry if I'm mistaken to pronounce your name as Gihan Eryukso. I'm sorry. It is very great, yeah. It is very great. It was very great explanation, and I think in the very young age, yeah, I have checked. You was born in the 2000, right? So now is less than 25 your age. So I hope that give my students motivation to follow your step, to pursue the doctoral degree in the very young age. Okay, and this is the certificate of appreciation for you. And I think your supervisor, Dr. Nazife, will very proud of you because you give a talk in this international conference, and as a representative of my department, mathematics department, we say thanks for you for your very valuable knowledge to share to our students and also all the participants. Thank you very much, and also thank you is a very great student from Dr. Nazife from HTP University. Thank you very much.
She's very hardworking.
Yes, of course. I see.
Okay, I wish all of you have a nice day, and for tomorrow, have a nice conference. If I can manage to wake up, I will try to attend.
Okay, thank you very much, Dr. Nazife. Yeah.
Take care. See you.
Thank you. See you. Yeah. MC, Mutia.
Okay, now we would like to the moment for a photo session. For our virtual attendees, please turn on your camera video as our committee will take the screenshot. Okay, we will take a picture with 3 images. In the count of 1, 2, 3, please take it. For the first photo, 1, 2, 3. Next, 1, 2, 3. And the last, 1, 2, 3. Ladies and gentlemen, now we are the final session of our virtual conference today. We would like to thank all participants, speaker, and organizer for making the international conference on computer science, actuarial science, mathematics, and mathematics education, ICCAMM 2025 a success. We hope you have enjoyed the session and found them valuable. We look forward to see you again at our future event. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, thank you very much all. So what time for tomorrow? 8 a.m. right? Jam 8 ya? Jam berapa deh besok?
8.30.
Oh, 8.30. Oke, jadi diingatkan semua ya, 8.30 ke peserta. Oke, thank you very much all. See you tomorrow. Ditutup aja dulu ya.